Okay.
Alrighty. Welcome everybody. Thanks so much for joining us today for the Grasp on Robotics Talk series. My name is Nikolai Matney. I'm an assistant professor in ESE. I'm part of Grasp. I'm going to be today's host. Just before we get into things, as a quick reminder, previously recorded talks can be found on our Grasp YouTube channel and website. If you're joining us via Zoom today, please submit your questions using the Q&A button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. If you're here in person, you'll have an opportunity at the end of the talk to provide your questions to the panelists. If you are asking questions at the end, please be sure to use the handheld mic when speaking so our online audience will be able to hear your questions as well. Today we have two student panelists from my group, Anusha Srikantan and Thomas Zhang. They'll be helping out with running the Q&A and taking care of your questions online as well. So I have the great pleasure of introducing Professor John Doyle from Caltech today. He's the Jean-Louis Chameau Professor of Control and Dynamical Systems and Bioengineering. So John has a illustrious career in controls and in research in general. He got his undergrad and master's degree at MIT, where he earned his reputation as a bit of a troublemaker within the field of controls, and then went on to get a PhD in math at UC Berkeley. Now you may be wondering why it's math and not electrical engineering. Well, it turns out he got kicked out of the engineering department for telling people that they were wrong during his quals exam. So, just to give you a little bit of a taste of John's perspective. During all of this, he was doing robust control as a consultant at Honeywell. And after he got his PhD, he decided that he wanted to pursue a career in Hollywood. So he moved to LA, and then as a day job, he took up a position at Caltech as a professor, where he also happened to be, at the time, the youngest person to ever get tenure at Caltech. He's won basically every prize you could hope to win in controls and IEEE in general. I won't list all of them, but some highlights include the IEEE Baker, which is for the best paper in all of IEEE. He's won the IEEE TAC Axelby Award, which is the best paper in control systems over the past couple of years. He won it 3 times, including 2 times in a single year, which is just unheard of. He also got World Top 10 in Mathematics Award, the Schuck. He also won an ACM Sigcomm Best Paper Award and Test of Time. Just to kind of highlight the breadth of his contributions, he's not just been limited to controls. He's really made fundamental contributions across a whole bunch of different things. Individual awards include things like the IEEE Hickernell, Centennial, and Control Systems Field Award. He's also, I think, one of the only people to give the Bodie Lecture twice at CDC. But if you ask John about his accomplishments that he's most proud of, it's usually related to athletics. So I kind of asked him which of his athletic feats I should highlight today. And so he said that for him, the big highlight was winning the time trial at the 1994 International Human-Powered Vehicle World Championship, riding for Berkeley. What made this really special was that Andy Packard was the team advisor, and the entire bike was built by Berkeley students, and John rode it. And they beat out a bunch of professional teams. They won the world championship, just to kind of highlight things. He'll probably be a little annoyed that I'll share this too, but he also likes to highlight that even as a over 40 masters, he had a PR of a bench press of 315 pounds, a 4-minute 45-second mile, a 2K ergo of 6.5 minutes, basically. Has a world record on the VO2 max of 75 ml per kilogram minute. If you have any idea what these numbers mean, you'll realize how insane that is. And he also ran completed a half Ironman in just about 4 hours. All right, so not only an incredible academic, but a just freak athlete as well. But if you were to ask John to highlight what his biggest contributions are, he will without a hesitation say that he's best known for his outstanding students, colleagues, and family, as well as the shortest abstract in IEEE history. There are none, for those of you who may have heard of that. So, before turning things over to John, I'd like to maybe just end with a couple of anecdotes. John was my PhD advisor. I get a lot of questions from folks about what it's like to have been John's student and what it's like working with him. So I thought I'd just share a couple of these before handing it over. So one is about the first time I met with John as a PhD student. I'm bright-eyed, bushy-tailed, clueless first-year grad student. Just finished a class on robust control, and I go in to sit and meet with John. And I'm excited to learn about what I'm going to work on. He's going to give me some, H infinity control problem or something like that. Well, the meeting started with him explaining to me that the internet is broken, just as a fundamental thing. The whole internet is broken, and we need to fix it. Then, somewhat of a fever dream of a conversation later, things ended with him recommending that I read Carver Mead's book on collective electrodynamics because physicists had gotten quantum mechanics wrong, and we should try to fix it. So yeah, that's a PhD with John in a nutshell. But a general theme of working with John, and I think it's important to keep in mind going into this talk, is that you'll be thinking about a problem and talking to him about something, and he'll give you some position or insight that seems completely outlandish and crazy. And you'll leave the meeting and you'll think, there's no way that's right. That's just crazy. Then you'll talk about it again a month later. He'll say the same thing. You'll think, okay, maybe he was a little right, but still mostly crazy. And a year later, you'll be on a walk or something, and you'll realize he was right the whole damn time. And that's really what it's like working with John. And he has just incredible breadth and depth and insight into really all areas of science and engineering. And today he's going to leverage those ideas and tell us about a universal theory of architectures that are basically applicable to everything. So keep in mind that even though things might seem a little outlandish at first, he's probably right, and we're all just catching up to him. All right, John, over to you.
Thanks for that outrageous introduction. I could spend the whole hour telling you what it's like to be Nick Motney's advisor, but you'll get a little of it. So this obviously completely crazy slide, as he suggested. And what I want to talk about is architectures. And so the idea is what are my current priorities? So the big priority is theory, and a few of them is system level synthesis, layering is optimization, learning and the interface with control, and then cyber and physical. But what I mean by that is we want to rethink how we do the cyber, but also rethink the physical in the context of this, okay? Cancer, neuroscience, microbiomes, biofilms, and then the social political stuff. And so the idea is that we need some rigorous theory for robust sustainability. All this stuff is evolved. It's not intelligent design, even though the designers, in the cases where they are geniuses. And natural selection produces things that look extremely well designed. So what I want to do is say, what's the simplest case study that illustrates these universal concepts in an accessible way? And also, I don't want to give a talk that Nick would just do better. And so that kind of cuts out a whole lot of stuff. So the theory is way better than me. So, which is what I would normally talk about. So what I'm going to talk about is I'm mostly talking about neuro, but if anybody's interested in cancer immunology, I could, spend the whole time talking about that as well. And so I'm going to talk about this paper, which appeared in 2021. And it's work with Terry Sanowski, who is, I think, the best American neuroscientist, maybe the best in the world, and appeared in PNAS. And Yori was the lead author. She's a professor now at Carnegie Mellon. And so we're interested in his layered architectures. Oops, what's going on? Oh, well. We're going to focus on brains. We could do a lot of other cases, so these are all interesting. Another interesting case is comparing cells with cell phones. Just kind of, it's not entirely a joke, but the idea is that they actually have a lot of shared architectures. And I made little cartoons at the bottom about what that is, and you're going to see that kind of cartoon over and over again. These are trade-offs. This thing, diversity enabled sweet spot, is a really key idea. But if you're interested in any of this stuff, we can do case studies very similar to what we're doing now on any one of these topics. And these are really great examples. So the most perfect architecture I've ever come across is that which bacteria has, and everything since then has been kind of kludgy. But the bacteria are really elegant, beautiful. But our cell phones are actually a good case study, and so both of those are really great examples, and I'll say a little bit about them, but mostly then focus on brains, which are really quite kludgy. So we publish in all these areas, and in fairly high impact science publications like Science Cell, PNAS, PhysRev letters, and so on. But not much acceptance of these ideas in science. So I've got a ways to go. So let's just talk about what we're doing right now, just to warm up, because this is a system that I'm assuming you in the audience know how it actually works. So we'd be doing all these Zooms, and we've got people doing the Zooms, and so I'm more interested in what's going on in the brains of these people than what's going on getting the packets around. But we know, for example, that while it looks like we're just talking to each other on our laptops and phones, in fact, there's an enormous amount of hidden architecture to get the packets there and to control them. Okay, and how does that organize? Well, there's lots of papers you can write, and I'm going to grossly simplify this. So the idea is that there's three layers. There's the app layer, there's the OS layer, and the hardware layer. And so how does that work? Well, this is all virtualized, so you don't see it. We don't notice what the hardware is, what the operating system is. What's really crucial about this is our ability to swap apps. So we don't have to write all our own code. We can just go grab it and download it and share it and then use them together. And so this is networked, swappable, and quite diverse. So there's an enormous variety of apps that we can access and use. And then once we have a shared app, we like Zoom, then we can use that. And basically, we don't have to know anything about what's going on to use the internet, pretty much. Okay, so the rest is all virtualized. So what's the next layer down? Well, it's the operating system. So the operating systems, whether they're in our PCs and phones or in the routers, are not diverse, and they're not swappable. So you can't easily just go, oh, I'm going to get a new phone. It's going to be a different operating system. I'm going to just move everything over. Actually, it's not that hard, but it's not as easy. And you don't swap the app. You don't swap the operating systems much of anywhere. You keep the operating system. And so it's not diverse. There's not many kinds of operating systems. There's only a few. And so then that allows for this virtual connection. And then finally, the OSs aren't actually connected to each other physically, of course. They're connected through the hardware. So you see this picture. And the hardware is a little more swappable than the operating system. So again, on your cell phone, you can swap apps easily. You can swap hardware a little less easily. And then the operating system is hard to change. But possible, just hard to do. But some places you can't do it. So in the internet, we're not going to change the OS, or we change it very, very slowly. Okay. So again, everything above the hardware is what I'm going to call virtual. I don't want to overload the term abstraction, because this whole thing is an abstraction. So I don't want to say this is an abstraction. Oh, and this other thing is an abstraction. I would say this whole thing is an abstraction. But what's going on in the system is virtualization. And so this is layered and virtualized. So here's what the hardware looks like, of course, what we're doing right now. And so from the hardware perspective, the people that are putting that all together, everything else is virtualized as well. So from both ends of the system, what your perception of it is massive virtualization. If you're doing the hardware, you don't worry too much about what the apps are. You worry about the operating system and vice versa. Okay, so same in the brains of the humans. So that's what we're going to actually go into more, is how the brains of humans work in this context. And so throughout, we'll get this. Okay, so we talk about this as an hourglass, and the idea is that it's an hourglass in diversity, not complexity. So the top end, the apps are swappable and diverse. The hardware is moderately swappable, diverse and swappable, and the operating system is not at all. Okay, so what case study would we use to most simply illustrate the consequences of these kind of layered architectures? Well, here's some of my favorite ones. And I mean, Lego's really good. Clothing is actually pretty good. Airplanes are good. Baseball's really good. Anyway, so, and this is what I would maybe do as well, but we think we have this is what we've been kind of doing for decades, but we have this new application to brains that I think is really fun. And so one of the things that's interesting that makes this architecture so powerful is horizontal transfer. So bacteria can just swap genes. So if one bacteria gets a new innovation, everybody can get it. Same with apps. So apps are very swappable. And that's what one of the things that this architecture allows. Okay. And so language also can be added to this. So language, what we're doing right now, we have a shared language architecture, and that lets us swap memes. Okay. And I'm going to giving you a bunch of memes here. Okay. So you can do horizontal gene transfer, you can do apps, you can do language, and all of them actually underneath have the same kind of layered architecture that we're going to talk about as being in the brain. So what can go wrong with this? And I'm not going to spend so much time on this because this is an endless story because everything goes wrong. But one of the ideas that this OS universality means that bad guys can hijack it. So what does a virus do? A virus comes in and acts like, it comes in and hijacks typically the parts of the operating system. And if you can get into that operating system, then you can take control. And that's sort of here is where the virus is attacked. And that's true. It's bad genes, it's bad memes, it's malware. All these things are exploiting the same fragility of layered architectures. And so this is one of the things we most have to protect ourselves again. And I'm not going to talk so much about this because I don't know how to solve it. And then when we look at human society and bigger things, there's horrible stuff everywhere. And almost all of this is hijacking infrastructure or architectures that otherwise give benefits. So we have to add values to this, and I'm going to not do this as much, but we have a new theory of social architecture, and there's really great animal models for it. So 3 of the smartest animals on the planet have social architectures. They're completely different, but have social architectures that share all the features that I'm going to talk about for brains, and that's a really interesting story, but that's a whole other lecture. Okay, so we're going to look at this. Okay, so this is the paper we're going to look at, and here's the concepts I want to get across to you: the idea of layers, laws, and levels, and those are the essential features that we're interested in. But we're also interested in sweet spots and diversity. So these are the concepts, and there's a person who's already kind of articulated this for a while. His name's Ray Jackendoff, and he's a linguist, and he calls it a parallel architecture because he says all these things are happening in parallel. Now, all we've done differently is just put math on top of all that. Okay. So this is why we have architectures. We want, and I'll explain what a sweet spot is and what diversity is and why diversity is absolutely essential to make any of this stuff work. So diversity is not something we do, because we like to be diverse. We do diversity because if we want to survive, we've got to do a better job of it. Oh, my cats are fighting. Hey, stop that. So here's our concepts, and why we build architecture is to create diversity sweet spots. That's why we have architectures, and this is how we do it. And so what I want to do is say, okay, let's take a really simple case study. You might think, why are human brains simple? Human brains aren't simple, but we can get humans to do things that are really nice experimentally. Hey, my cats are causing trouble. Sorry. So this is also a sweet spot. It's a universal story, but it's fairly accessible, and the experiments are easy to reproduce. It's all high school algebra. We figured out how to do all the theory with high school algebra. So, okay. So this is what we're interested in. Mountain biking down a twisty, bumpy trail. Okay. And so you got the trail, and you have a layer in your brain that controls this process, and it's slow, accurate, flexible, and so on. Okay, it's conscious, it's deliberate, and it has stable virtual dynamics because you have another layer that takes care of that, and this is using vision. And then there's the bumps, and you actually have a layer for that as well. I'm kind of oversimplifying it, but this is fast, it's inaccurate, it's fairly rigid, it doesn't do a lot of other things. So you're using the visual layer to actually read this slide, not just ride mountain bikes. Okay. And this deals with the unstable real dynamic. So completely opposite from these two layers are as different as can be. Okay. So the idea is that what you would ideally like to have is this, in this corner, you'd like to have a system that's fast, accurate, and flexible. Okay. But as we're going to see, we don't have any parts that are fast, accurate, and flexible. So how the hell do we build this? So we'll have a theory that explains how we think the brain works on this. And the idea is that what we'll see is that the hardware has a severe trade-off. You can be fast or you can be accurate, but you cannot be both. So ideally, you just be in that corner. So what do you do when you're in this situation? Well, you build the right architecture. And that right architecture, turns out we split it into layers, a trail layer and a bump layer, and we'll go through how that actually all works. And so what you have is that you have a subsystem that's fast, a subsystem that's accurate, and then then what architecture does is combine those in a way that they work together so that the system is fast and accurate, even though the parts are not. And of course, we can't get IRB approval to crash bikes in the world, so we had a video game. And this video game is easy to get, it's easy to reproduce, and actually, it turns out to be a great platform on which to do all sorts of neuroscience experiments. And also, you don't have to be a neuroscientist to do this. I mean, this is, again, high school students have done everything I'm going to have done everything I've told you. I mean, they didn't come up with it, but they were able to reproduce everything I'm going to tell you. So I'm going to tell you about these pieces. And oh, by the way, I'm not going to spend a lot of time. If you look at the paper, the data and the theory they fit so well, it looks like we faked it, but we didn't. But it looks like we photoshopped the whole thing. It fits so well. Okay. Now we're going to focus on this trade-off, which is speed accuracy, but there could be a lot of other dimensions that we can project into two dimensions pretty well. And it's sort of like doing PCA on the space of concepts, so principal concept analysis. So I'm not going to talk about all this, and I'm mostly going to focus on speed and accuracy, but there's a whole bunch of other trade-offs that are just as interesting. So I've told you what layers are. Layers are a trail layer and a bump layer, and those stack on top of each other. But there's another thing, which is the system level and the nerve level. And this is completely orthogonal to the layers. So the idea is that we have the system level where we're describing how the system works overall, but then it has to be implemented in spiking neurons. And so we've got to connect these two. Okay. So this is going to be our model in the upper right. Our model in the upper right is this picture, but it splits into a trail layer and a bumps layer. So you can, and here's the amazing thing, is you can solve these separately, and then you stick them together, and the combination is optimal. So you could solve this directly, solve these individually, and you get the same answer. And that's what you really would like to have in a layered, leveled architecture. So the layers are just splitting this into these two boxes. And you can sort of think this is guidance and control in the old days. And there's a navigation that's already been done. We've already decided what the trail is. And then we just have to follow the trail and do it while getting bumped. Okay, so the system level is connected to the nerve. So the other, again, orthogonal to layers is levels. So layers is, at the system level, you're splitting the system into two layers. And then you have to build that out of nerves, okay? So it turns out one of the things that's nice about this is this relationship is particularly simple in the case of brains. So what happens is the accurate layer is implemented in the nerve level with accurate nerves, and the fast with fast. So what that does is allows you to exploit diversity in the nerves to create a sweet spot at the system level. And that's the whole point of architecture. So we could go through anything that we have, is that we could create this diversity sweet spot. And that's true of the internet, it's true of our brains, it's true of our cells. It should be true of society. We're doing a bad job. So that's the level story. And every level and layer has its own laws. So when I draw these little pictures in here, and what I mean by that is there's hard limits on what you can actually build. So at the nerve level, there is no fast, accurate nerve. It'd just be prohibitively expensive. But what you have is you can have either fast or accurate. But then the idea is that if you combine that, the trade-off at the system level is better than at the nerve level. And that's what architecture does. Okay. And only the right architecture can create these sweet spots. Okay. And so we were able to make this model, which was just all high school math. And what you can do is you make this block diagram in the upper right. You solve for the things in the boxes, and you can solve it either two ways. One at a time, separately, or all together, and you get the same answer. And what we're going to have to talk a little bit about is what is our model for what nerves can and can't do in this context. Okay, so this is the theory, and I just showed you all of the theory, and the question is, can you derive this? Well, you could get fancy and bring in all sorts of heavy machinery, but we tweaked everything. Like we tweaked the experiment, we tweaked everything so that you could do this with high school algebra. And the idea is that most of the audience for this is never going to believe it or understand it. But if we can explain it to their children, maybe their children can help them understand it. So that's one of our motivations. And so there's the elements of architecture. Okay. And as I said, layers, laws, levels. Okay. So let's look at the nerve level. Okay. So how do nerves work? Well, we're going to think of a nerve very schematically as this thing here. And what it is it has a whole bunch of axons. Okay. And then a whole bunch of infrastructure to support the axons. But the real issue is the signals are going on axons. And so one of the ideas is, what do nerves look like and what diversity do we see in nerves? And so what we see basically is a picture that sort of looks like this, and I'll try to explain this. So let's just look at some nerves, the cranial nerves, to just get a feel for what sort of diversity you see. Now, it turns out these cranial nerves are all about the same overall size. So they only differ by their composition. And we're going to see that they differ quite dramatically in composition. Okay. So here's a picture of the cranial nerves. And so what I'm showing you is, on the x-axis up top here is the number of axons per nerve. And then on this axis is the average axon diameter. And there is some diversity within the nerves, but not as much as between them. So I'm going to pretend they're homogeneous. So what you see is, orders of magnitudes. Why is this doing this? Orders of magnitude differences between these. And we're going to focus on optic and then something that's down more here, reflexes. So there's a million ways to do really cool demos, and we could do a live demo with you to show you how all this stuff works just by playing around with you in the audience. But that's hard to do remotely, so I'm going to stick with our game. So here's the idea, is that you can either have a lot of axons and then you're accurate, or a few axons and you're fast, but it's prohibitively expensive to be in this corner. So there's this trade-off. You can have either a lot of little ones or a few big ones. Okay. And then it turns out you can directly connect this with this model, which is the bandwidth is proportional to the delay. Really simple model. Now, we didn't come up with it. Well, the authors on this paper didn't come up with this. The person who gave us this model really was Simon Laughlin, but his main collaborator is Peter Sterling. And I mentioned Peter Sterling for two reasons. I've not collaborated with him. I've met him, but I've not collaborated with him. But I would say if there was anybody in biology and neuroscience that I have not worked with directly, who's had the biggest influence on me, it's Peter Sterling. And so he's had an enormous influence on this work. But also, his career was at Penn. He was a professor at the Penn. He's now a farmer in the mountains of Panama. So I finally got to meet him last year, and I mean, for me, he was a god as a scientist, but he's an even better person. And so he's just unbelievable. I'm a huge fan of Peter Sterling. I wanted to mention him because he was at Penn. So here's the idea. We have this model, and it's a trade-off between bandwidth and delay, or speed and accuracy. Okay. So what did Turing and Shannon do? They actually did this, in retrospect, something kind of draconian, which you would think is they would say, okay, Turing said, let's not worry about bandwidth. We're just going to worry about delay. Let's assume memory's free. And his original Turing machine had an infinite tape. Shannon took the other end. He said, let's not worry about time. Let's just worry about bandwidth and accuracy. And both of them sort of then let T go to infinity, and then you actually don't worry really about delays. So what we need is to combine the two, and Bodhi does that. But we need an upgrade to Bodhi to do this. So the idea is what we want to do is combine both the Turing picture and the Shannon picture. And that was just previously intractable. And Nick has contributed a lot to overcoming this intractability. So the system level synthesis overcomes this. And again, the system level synthesis is probably maybe the most interesting thing I've worked on. And I'm not going to talk about it because Nick knows it better than I do. And so just as an example, one of my most recent student graduates got her PhD last year, Carmen Amo Alonso. She got the prize for the best thesis in all of Caltech, which is hard to do if you're an engineer. And her thesis was based on 8 papers, and I was a co-author on one of those papers. And they asked, like, well, who did she work with and who was her main co-author? Well, it was Nick. And so my student, when a student like that comes in and she's looking for advice from her advisor, my advice is, oh, here's a cool problem, and see if you can get Nick to help you work on it. And that's my most successful strategy. So now my students, of course, I tell them to work with Carmen also. And so Carmen is just blowing up the whole subject of linguistics in a really fun way. So, but totally intractable. We fixed that now. But I'm not going to talk about SLS because Nick can talk about it better than I can, and I want to try to focus on what can I say about the neuroscience. Okay. So here's this trade-off between speed and accuracy. Now, I'm not going to justify this. I just got this from experts. But the idea in spiking neurons, you can either have a lot of axons, very accurate but slow, or you can have a few axons and fast, and this is the trade-off. And so the justification for this very simple trade-off is not simple. And if you want to see what the justification is, Sterling and Laughlin have a book. It's fantastic on how brains work. But we didn't get it from the book. We got it directly from them. And we had some god-awful model, and we showed it to them, and they just laughed and said, okay, here's what it really is, and it's way simpler than what you think. And so that was very helpful. Okay. So now what we're going to do is we're going to say, okay, if this is what nerves can do, and we can build a system out of this diversity of nerves, what would we do optimally at the system level? Okay. And again, the data fits the theory perfectly. So what you do is you use this model to constrain the hardware. Then you solve for the optimal controller. And I'm not going to go through the details of this in 2 ways, right? You solve it for the whole system, and you get the optimal control. And that's easy to do, and it's high school algebra. But then you can say, oh, what if I just solve for them separately? I'll just solve for and we can do this experimentally. You can just have the bumps, or you can just have the trails. And you can solve for them separately, and that also gives you the same thing. Now, this is a whole another talk, which is this depends on humans being good at multiplexing these two. So they do the two in combination as well as they do each separately. And oh, by the way, Nick was one of our better subjects. He was quite good at this and learned it really quickly. So that was kind of a miracle. But then now you might ask, okay, so what was interesting about that? This said that given this hardware constraint, this is as good as you can do. And oh, by the way, humans achieve that. But it means they have to multiplex this well. If you add texting, they crash, right? So it's a very carefully selected problem. But on the other hand, it's the heart of how our brains work, in the sense that we have this unconscious, automatic, fast reflex stuff all the time, in language, in everything we do. And so we found the simplest case of that. Now, of course, in reality, there's other things we're very interested in beyond that. So what is this? Well, it's one dimensional. We got a scalar trail. We got a scalar bump. So we haven't said anything much about how the brain actually does implement this, other than we've said it's damn close to optimal given the hardware available. And the hardware is so slow. You think, how can you do anything with this slow hardware when you're used to speed of light electronics? Well, it's amazing what the architecture allows you to do. Okay. So the idea is that what you get is this, you get this diversity sweet spot. In general, you need SLS for these kind of problems, but in this case, we didn't. Okay. But here's the problem you really end up with normally, right? Not this simple little toy thing, which is the lower layer reflexes look like this. And I'm not going to spend a lot of time on this. But in order to do these lower layer reflexes, we need SLS. And before we had it, this was just hopeless. And so that's the picture we really care about. So what do the bumps layer really look like? The bumps layer look like this thing in the lower right-hand corner. Okay. And I'm not going to talk about that, again, because Nick, he doesn't know as much about the neuroscience as I do, I think, at this point, but he knows a lot more about the theory. So that's this paper, but we want to go deeper, right? So the question is, in this picture, vision, all of vision was just a box, right? But here's a little more detail on what's going on in these boxes, okay? And this is kind of a standard picture, which is you have the retina, then you have the thalamus, and you have V1, V2, you have the motor stuff, you have more motor, and then you finally actuate. So this goes out to the muscles. Grossly oversimplified. But what we want to do is say, okay, we've got external feedback here, which is what we modeled. But in fact, there's enormous amounts of internal feedback, the stuff in red. So the internal feedback is more complex than the forward path. And this has been confusing, because if you think about this all from an information theory point of view, you know that internal feedback doesn't add anything to mutual information. And so why is this there? And the reason it's there is because of all the delays, but we want to really nail that down. And to do all this, again, you need system level synthesis, but Lisa figured out a way to at least make a first cut at this using old control theory. So this is this paper, also in PNAS. And so Lisa is the first author. She just finished and is now a professor at Michigan. Anish, all of this was his idea, basically. And she sort of came up with the technical picture that avoided SLS. So we first solved everything using SLS, and then she figured out, oh, if we make very special cases, we can get without it. Okay, so, and Anish now is in medical school. So he decided he wants to be a physician scientist. He's also our expert on cancer. So if I had time, I would tell you the amazing things he does with cancer. Okay, and these are old pictures, right? I mean, so these pictures are basically the same. The one on the right doesn't have arrows, but when you put the arrows in and simplify it, you get the picture on the left. So what Lisa came up with was, this is an LQG model. And the key thing is, if you put sensor and actuator delays in, so that's visual cortex, and that would be motor, you get an enormous amount of feedback internal to those processes. And you get that from LQG. And that was a surprise. If we put delays internally, which there are delays internally, and this is just a Kalman filter, then you need SLS, which we didn't need with fast electronics, right? So we didn't need to worry about the blue lines in airplanes. We just need to worry about the other stuff. Okay. And system level synthesis deals with this problem. And so I'm not going to say much about it again because Nick says better. But the idea is that once you get to these lower layers, everything is sparse, delayed, and quantized. Sensing, communications, computing, actuation plants. And this was a complete nightmare ever since Westinghouse, if you've heard the name Westinghouse. So this SLS is, like I said, probably the biggest breakthrough for me in 50 years. And so you can now have a layered architecture that has a centralized planning, but also this distributed reflexes. Okay. And we didn't need that. Now we do, because biology is cheap and slow everywhere, yet it works really well. Okay. So that's the picture we want to do here, but we're going to defer that. Okay. So that's our current focus in our research. But let me tell you what we did so far. So in that case, everything, you have these layers, you have everything sparse, delayed, and layered, and so on. So this is what we used to do. And then if there was any delays, it would usually be in the sensors and the actuators. But internally, our communications, our computing was all speed of light, controlling a system that's speed of sound. So the delays internally didn't matter. And that's completely changed. And then you need SLS and you basically need NIC. So how does this work? Well, I'm gonna be a little sloppy here and just tell you vaguely how it works. So the idea is that what you can do, which is a miracle, is you can zoom into patches. So you don't have to look at the whole system all at once. You zoom into patches and you design with patches and you implement with patches. So that makes everything order one scalable. And so, like I said, I was shocked that any of this worked, because mostly I was telling Mickey and Nick. Nick was kind of the main advisor on this work, even though I was his advisor. And the idea is that what you want to do is you want to have global goals, but you do everything locally. And that makes it scalable and implementable. And so we're going to not go into that detail. So another talk, but again, like I said, Nick knows this better than I do. So talk to him. Okay. So let me just say a little something about cancer. The idea is that how do we apply all this to cancer? Well, the immune system and the cancer that you're fighting all have layered architectures. And they have speed accuracy trade-offs, just like we've been talking about. And it's essential to understand those speed accuracy trade-offs if you're going to understand how to do, say, cancer immunotherapy. So if Peter Lee's City of Hope, this is one of his papers, how can we help in this kind? So this is ivermectin and cold tumors and hot tumors and immune checkpoint blockades. And his interest is breast cancer. So he does mouse experiments, and then he's doing clinical trials with metastatic breast cancer, which is a nightmare. And so he has this picture, and we're trying to say, what we're trying to do is connect wounds with cancer. So this is a really old idea. Tumors are wounds that do not heal. That isn't quite true, but it's a really great idea. Okay. So here's one of the things that I'm going to say a little bit about, and I'm not going to go into further details, but it just brings up a way of thinking about this. So this is this picture from Uri Alan, and I should have given him credit for it. I left out the slide. But here, what's plotted here is, and I've added these kind of things on top of it. I should have been a little more careful. But the idea is that this shows all sorts of animals. These are all birds and mammals. And this is their mass. And they go from like little tiny shrews to whales. Okay. And here's an elephant. We like elephants. We like elephants a lot. Okay. So what you see is there's this little triangle here. If you're in Santa Fe or Boston, this is a power law, but we think it's a triangle. Anyway, so the idea is that at the top, you have very long life. And so there's this thing called Peto's paradox, which says these long-lived animals, especially the big ones up here like elephants, should have cancer, right? Because you got this huge elephant. It lives for 80 years, or at least the females live for 80 years. And think of the number of cell divisions, et cetera, et cetera. You got to get cancer. There's no way you can build an elephant. Okay. But what we noticed was, yeah, all these guys up top have left cancer, but they have really weird wound healing. But they can get away with having poor wound healing because they don't experience violence. Either they fly, they burrow, they're social, they're big. So if you're an elephant on the savannah, you have a big family, and you're the biggest, baddest thing on the savannah, you don't get wounded because you don't have predators and you have extremely thick skin. So you don't need to heal wounds well. Now, elephants in zoos are a nightmare because they do get wounded, and then they're very hard. They don't heal well. Okay. So that's this big picture. So we came up with a theory that says we think this is some essence of cancer, and here's a trade-off between wound healing and cancer. So you can either have good wound healing and you're going to get cancer, or you can not get cancer and have poor wound healing. So this is our theory, right? Well, somebody comes along. I mean, so you show it to experts. And also I said this only matters for females because males are expendable. So the experts come along and say, well, this is okay for orcas and elephants and mammals and birds and stuff. But jellyfish, sorry, they don't get cancer. They're immortal and they heal really well, right? So it can't apply to jellyfish because they don't have any of the features you're saying. There's a trade-off there, and we're fine. Here's an animal that doesn't have the trade-off. Okay, so and every carcinogen has been tried. Everything has been tried on these animals. So experts are absolutely certain that it's not possible that these get cancer, and therefore our theory can't be right. Okay, so no trade-off. Well, Anish, using our theory, said, well, let me take a look at this. And so on the left is what happens to jellyfish if you give them carcinogens. Basically, it turns out nothing happens. Okay, so you give them a carcinogen, nothing happens. So you give that carcinogen to us, and we die. Okay, or practically everything dies. Okay, but here's the thing: is the theory says if you inhibit apoptosis, which is this CASP inhibitor, and give it the carcinogen, you get this freak out, which is, who knows if that's cancer, but it certainly looks like cancer. So, it looks like cancer, walks like cancer. So we're just going to call it, potentially, or I guess what's the right word for it? Oh, I'm sorry, I forget the word. It starts with A. Anyway, so now this is just jellyfish, and we're going to try to publish this, but you have to really be careful because no one's going to believe it. And so, but the idea is that the same theory applies to us. And so now we can start looking at what do we do? And we have to look at healing and inflammation and all this stuff. And so the idea is that I'm going to only say this really quickly because this is just so I'm going to tell you the mainstream view slightly tweaked to fit our theory. So these are the stages of wound healing, and I'm not going to say a lot about it, but there's stages and then there's levels. So stages is another thing, which is when something goes through a series of things, it's called stages. So we have levels, layers, and stages. And here's the levels. Here's all the molecules involved. Okay. So how does this get hijacked? Well, it turns out those same stages and those same cells get hijacked by the tumor to create both tumors that survive this immune system typically just kills everything. So you never even notice that you've got maybe a cancerous cell because the immune system just kills it. But there's a hijacking, just like the hijacking of the internet or anything else that involves layered architectures. You can hijack it and turn wound healing into cancer. And so again, this is absolutely standard mainstream theory or main theme thinking about this. And so what we want to do is have a theory that explains, more precisely exactly what's going on here. And so we talked about these universal architectures and where you have the speed accuracy trade-offs. Well, it turns out the same speed accuracy trade-off occurs inside our cells and inside our immune system. And so at one extreme, you have a internal thing called sting, which even bacteria have. And what they then do is recruit cytotoxic T cells, which takes a long time. But there's all sorts of stuff in the middle. So there's this, anyway, I'm going to skip all this. But the idea is that there is this layered architecture, speed accuracy trade-offs. And this is exactly how I think that, the best immunologists think about this problem. But they don't have any math for this. But now these kind of layered architectures, all the math I've told you up to now applies to this. So we're now trying to figure out how does all of this work, and that's kind of one of our big themes right now. Okay, so I'm going to skip ahead, I guess. Okay, so lots of stuff. Okay, so the idea is that the nervous system, the immune system, creates this diversity sweet spot by combining all of these different components, just like we saw with the nerves. So you have really fast stuff, you have really flexible and accurate stuff, and then you have everything in between. And again, this is exactly the same example where we get this diversity-enabled sweet spot. And again, what goes wrong? This gets hijacked. Okay, so just like viruses hijack our cells, tumors hijack this immune system, and some of our pathogens also hijack this immune system. So AIDS hijack this immune system. So we see a battle between this layered architecture and attacks by cancer or pathogens that also have a layered architecture. So if we're ever going to develop a theory that really nails this down, we're going to have all the elements in much more complexity than I talked about for the brain. And obviously the brain, if we want to understand what's going on inside, we also have to have a lot more complexity. Okay, so let me, I'm kind of out of time, so let me skip to, let me just see what else I got here. Okay, so yeah, this is trying to explain more details. Okay. Yeah, so sorry about that. I have videos online about all this, and if you're interested, I can point you to them. Okay, so anyway, so we're going for therapies. Okay. Again, but we always ask, like, what can go wrong? And what about the larger societies? So you can imagine, some alien robotic AI landing on Earth and looking around and just doing principal component analysis on everything that's going on. And so they happen to have landed in Texas. And so they figure out the biggest PCA is men like to kill women and children. And they'll go, oh, that's weird. We don't do that on our planet. And then they go, well, that must be just Texas. And the Americans, so they go to California, no, that's just Texas. And then they go to, Gaza and Ukraine. They go, oh, it's way worse there than even in Texas, right? So we got a big problem. And this is just a toy cartoon of some of the elements of that problem. So the question are, like, if you look around this world, it's like, are there any good examples, right? So it turns out there are. And I'm going to only say a little bit about this, but this is one of my current hobbies, which is the elephants and the bonobos and the orcas. The elephants up top, the bonobos on the left, and the orcas here. And what I'm putting here is what they don't do. There's no warfare. There's no infanticide. There's no cannibalism. There's violence. I mean, this is the top predator probably on the planet. So they are extremely violent. And, come on. But they aren't run, none of these are run by fear and anger. That's not the way there's no bullying. Okay, and they're three of the smartest animals on the planet, the other two being chimps and humans. And the reason these are all these are all lines drawn through them that they don't have, it's because chimps and humans have all of them. Chimps are really nasty, but we're like chimps with nukes. Okay. So what I've been developing is, again, a whole layered architecture theory for how this works and why it works so well. And we could talk about that endlessly. It's kind of one of my new favorite topics. But but I've been told by my colleagues that I shouldn't ever talk about this in public because, and they're right, it's a good way to get yourself killed. So I've decided I won't, because it turns out both the left wing and the right wing hate this whole story. Okay. But you can at least guess one thing that these things have in common, and I'll leave it to see if you can guess the most important thing they have in common. So the question, though, is there any story in humans? And two of my most favorite books that tell as good a story about what goes wrong in humans as I can think of are these two books. They're quite recent. And this cast has been turned into a movie called Origins. And even if you read the book, um, the movie is fantastic. It was for me just because it made it much more visceral. Whereas if I read the book, I've not experienced any of these things. How do I don't have any feel for it. I can try to have empathy, but I haven't experienced the stuff that she's talking about. I know it exists, but the movie really makes you feel it. And these are complementary. They tell orthogonal stories, but together they tell a more complete story. Okay. So I don't have a path to go from where we are to fixing all this crap. Nor do I have a new therapy for cancer yet. Okay. So what we're trying to do is figure out what's the right way. How do you deal with metastatic breast cancer, for example? Because the patients that are at that stage are going to die for certain. And so one of the reasons they're trying all sorts of exotic therapies on them is that they got months to live no matter what. What you're trying to do is see if you can fix that. We can't do those same kind of experiments here. And I think basically nothing else matters if we don't fix this stuff. And so I wish I could say, oh yeah, we know how to cure this. We know what a good system looks like, and we know that we know what a well-functioning physiology for a human looks like. But if they have cancer, steering that back to the healthy state is hard. But I think we need the kind of theory I'm talking about to do that. But I don't want to, the problem is I don't want to spend a lot of time on more details about this because it's a mess, and every part of the political spectrum is not going to like what the theory says. So best to not talk about it in public. Anyway, I think I'll stop there and see if there's any questions. Maybe I'll turn my video on. Okay, questions. I know that was insane. I apologize. This is what Nick.
Hi, thank you for the talk. So I have a question about how you were able to try to like generalize the theory across different domains. One of the questions I have is when we talk about, say, one agent, one animal, or one person, there's a clear objective, say, I want to make more money, I want to survive, or I want to live better. But then if we try to think about this from the social perspective, it's really hard to tell what a society is trying to achieve. It's more like a, like evolution, right? Or are you talking about this from a government perspective on how this theory can potentially transfer to these more complex systems?
Oh, that's like, okay. You just asked the perfect question. What we in both the brain and the uh, what's going on?
You dropped off for a bit, but you're back now.
Oh, okay, sorry about that. Okay, so the simple assumption we make in combining robust control theory and SLS is that there's two kinds of agents. There's your team and there's your enemy. And the teams are all on the same side. The enemies are all trying to do as bad as they can against you. Okay. And that's actually not a bad model for a lot of situations. It's actually not a bad model for cancer. You assume the immune system is all on your side. You assume the cancer is all against you, or the virus is all against you, and then you see what happens. And what you have to add in is that, in fact, the viruses and the cancer actually turn some of your teammates against you, and so does autoimmunity. And so, so this is for Nick. Nick, we need a theory where the agents are not just pure teammates and not just pure enemies, but where they're everything in between. So they all have their own goals. Some of them align, some of them don't align. And so we've only ever studied situations where they're either totally on our side or totally an enemy, with the same objective, which is in a min-max theory. So what we really need, one of the biggest things we now need to add to this whole framework, is a more nuanced view of what agents' goals are. So that was a perfect question. And almost everything we're studying now, whether it's mental illness, whether it's cancer, the immune system, or society, has this mix of agents. And it's almost unavoidable. So the problem is, if you build a really good T cell to really do a good job of killing infected cells, whether they're cancerous or viruses, it's very hard to keep it from sometimes going off and killing you with autoimmune disease. And that's a trade-off space that we're starting to understand, but we really need an upgrade to control theory, just like we did. But SLS was an upgrade to control theory that let multiple agents cooperate with limited communication and delays. Now we need and robust control was about how to be robust against a whole bunch of adversarial agents. We need a theory now that says, yeah, but there's all sorts of stuff in between that we'd like to characterize more crisply. Sorry, long answer, great question.
Hi, John. So we had a question from earlier on in the lecture. The question reads, can you articulate why we need diversity sweet spots? I think you might have answered this over the course of
I tried to, but let me say, so here's the problem: is we have a problem we want to solve. And we look at our hardware, and no piece of hardware solves that problem. And then you go, could we build a single piece of hardware that would do what we're doing now? You know, just one kind of box. And the answer is no. So the laptop that I'm using, and the computers you're using, and the routers in the internet, and if you're watching this on your cell phone, there's enormous diversity in all of that hardware. And there's enormous diversity in what we want to run on that hardware. We don't just do Zoom, we do a lot of things, right? Eventually we're going to run the whole planet on that infrastructure. And that will add a whole nother pile of problems. Anyway, so the idea is that we need diversity. We have diversity in what we want our systems to do, but no part does everything. But if we combine the parts in just the right way, we can get this sweet spot where we get properties that no part has, but in combination they have. And so what you want to do, of course, is combine fast and accurate parts to get a fast but not accurate, accurate but not fast, to get a system that's fast and accurate. Of course, what we often do is we take, fast and accurate and combine it to get slow and sloppy, right? That's not what we want to do, right? But you need diversity of functionality, and you need diversity of components, and you need architecture to connect the two. And only a layered architecture does that, at least both theoretically and in practice. So that's the point of diversity. So diversity isn't something nice to have for social justice or anything like that. Diversity is really essential. And unless we get diversity properly used in society, we're dead. And we don't have it now. But the elephants and the bonobos and orcas already do it really well. So at least we have model organisms. So like we're studying metastatic breast cancer in mice, we have a good model organisms for studying social architecture.
Thank you, John. There's another question by Professor Baiji that reads, John, wonderful lecture. It is known that neurons have multiple options to connect with other neurons. Do you know of some plausible decision-making in how they select these other neurons?
Oh, yeah. Well, normally I just say, okay, Terry, could you answer this? But Terry's not here. That's a great question. So what we are not doing so far is looking at development or synaptic plasticity or all those mechanisms. What we're doing is saying, suppose all of that is done perfectly. So evolution, learning, everything is done perfectly. The only problem is you must build it out of this hardware. And what we're saying is, if you do all that right, here are still the fundamental limits left. Now, the obvious question that we're now working on is, but we're basically viewing the nervous system as a packet switch digital network, right? And so a crucial thing to do is say, let's go beyond the Sterling models of spiking neurons, and let's look inside a little bit more, and let's look at how, what synapses are doing, how development and growth happens. So those are all on the frontier. And so, and absolutely it's really important if we're going to understand the brain, because some of our disorders are just, bad wiring. And then what do we do to fix bad wiring? What do we do to fix the problems associated with a stroke or anything else like that, or any kind of aphasias in language? How can we understand them and also help treat them? And you got to go way beyond the model, these toy models. So these are absolutely this, again, our objective was to make the first thing, everything could be done by high school students. The next thing was everything could be done using, 1970s control theory. You didn't need all this new robust control, anything since the 70s. Because most people actually, so it's really bad, which is like robust control appears to be the worst taught subject ever. And I think take blame for that. So we still got to get robust control into this picture. So there's a lot that has to be added to this, but absolutely more details about how neurons grow, how they connect is really important. One thing is they're really sparse. No matter what, you have, billions of neurons, and you have each one of them has connections of a few thousand. So extremely sparse and delayed. So getting sparsity and delay into the picture is essential, and that's what we started from. But everything else is still open. But I think this is the right way to start thinking about those questions.
Time for one more question, if there's any in the audience. Okay, I have a question, John. So one question I have is, let's say we have a theory of getting optimal layered architectures for a particular application, but currently the way things are implemented is already fixed. And let's say, for example, you had these applications of connecting computers over Zoom, where there's diversity. So people are going to be slow to change that architecture because they already have a solution that works, right? But you have a theory now that says, here's the optimal thing to do when you connect these architectures, or you have some, let's say, way to quantify that. Or do you have a way, does the theory have a way to quantify what people are losing from not doing it the right way, I guess is my question. So
here's what we're pretty good at, is upgrading the algorithms within an existing layer. So improving TCP.
Mm-hmm.
Good example. Okay. And we hope that we'll do the same thing with cancer immunology. We'll be able to, we're not going to change the architecture at all. All we're going to do is tweak the algorithms that are running in cells. Okay. So most of the use of this is not going to be to design, fresh new architectures, but to try to upgrade the ones we have. And the math to do that is well developed. The problem is some of these architectures are fundamentally flawed. So what you'd like to be able to say is, what happens if you don't just change the algorithms within a layer? Or just get you a little faster hardware, or a little bit algorithms running at the application layer. So we all this stuff in machine learning now is constantly improving, and they are bringing in new hardware, right? So the chips that are being used now heavily is new hardware. It's been improving over the last several decades. So you want to be able to have that kind of evolvability, and the architectures we have around us actually have a lot of that. So even though the internet architecture was not designed with a theory, in fact, it was anti-theory, because the theory was information theory, and they said, let's throw all that crap out. We're not going to use information theory at all. We're going to do this whole new thing with packet switching. And of course, all the experts said this won't work. So they were really artistic geniuses, but they had no theory, so they made mistakes. But when you look at it in retrospect, it's fantastic. I mean, it's brilliant. And then you look at bacteria, and they're fantastic. And there's no designer, at least according to me, and most of my colleagues, there's just evolution. But both of those processes yield extremely good architectures, partly because I think they don't work unless you have a good architecture. If you don't have the basic architecture right, it's not going to work at all. So initially, what we're going to be doing is trying to tweak the algorithms. And this is, again, something that Nick has been interested in and I'm interested in but what if you had a clean slate? What if you could actually have different layers? What would you do? And I would say, actually, we're not as good at that right now as redesigning algorithms within the layers. But that's a frontier. So that's another frontier, which is full-blown, top-to-bottom, full-stack design. And again, Nick is kind of one of the experts on that. But that's kind of good news and bad news, because it means that, we both this problem of agents and alignment of agents and how to do the full architecture design in an integrated way, that's a big challenge. And we haven't solved all of the necessary math to do that challenge. But that's like that first question. That's a great question. That's exactly what we have to start doing next, which is diversity in the agents, not just friends and enemies. And also then, what if why not have a 4-layer architecture? Why not have a 5-layer architecture? What would you put in addition? And of course, we're wedging layers within the internet all the time, but we'd like to have a theory that tells you how to do that and not just rely on artistic geniuses. The problem is, if your architecture is always done by artistic geniuses, they're going to make colossal, civilization-ending mistakes. And so we want to have a theory so we can avoid that.
All righty. Thanks a lot, John. That's it for today. So let's give John another round of applause. And just in closing, let me ask those of you both here and online to please tune in next Friday, February 9th at 10:30 a.m. Eastern Time for our next Grasp on Robotics talk featuring Dr. Chi-Ching Huang from the University of Texas at Austin. For more information on upcoming events, be sure to follow us on social media or check out our website. Thanks a lot and have a great day, everyone.